Hello, this paper presents a scheduling scheme for efficient wireless charging of sensor nodes in wireless body area network, which is called shortly WBAN. The authors of this paper are Mohammed Karam Moni Rabi, Mohammed Shah Alam, Shamim Ara Shawkout, and Mohammed A. Hoke. This research was conducted at Bangladesh University of Engineering and Technology, in short called BUET, Bangladesh, in collaboration with the University of Tennessee, USA, and East Tennessee State University, USA. I will structure my talk as follows. First, I'll introduce wireless sensor nodes and body area networks. Then, I'll define the specific problem we're addressing and our research objectives. I'll cover the basics of inductive powering and our proposed saturating Class C driver circuit model. The core of the talk will be our novel scheduling algorithm for charging nodes. Finally, I'll conclude with our findings and future work. Wireless sensor nodes are the fundamental building blocks. They are autonomous, distributed devices that can harvest small amounts of energy from their environment, typically in the milliwatt to watt range. However, their major limitation is energy storage. Their small batteries deplete quickly, especially in continuous monitoring applications like healthcare. A WBAN is a time-critical, sensitive network worn on or implanted in the body. It consists of a central coordinator and multiple sensor nodes deployed at various positions. Its applications are primarily in medical services and consumer electronics, enabling human-centric wireless communication for continuous health monitoring. This slide shows our system model. Sensor nodes collect data and transmit it via a medical implant communication service linked to a central controlling unit, or CCU. The CCU then relays this information over long distances using web-based internet or GSM links to a medical environment, enabling remote patient monitoring. The problem is visually clear. We have sensor nodes at critical locations like the chest, wrists, and thighs. The key challenge is establishing an efficient charge mechanism between the controller and these sensor nodes. How do we wirelessly power these numerous, spatially distributed nodes without wasting energy? The limitations are twofold, as cited from prior work. First, there is a fundamental power scarcity in wireless sensor networks, shortly called WSNs, due to small battery sizes. Second, there is a notable unavailability of an efficient charging scheme specifically designed for the dynamic and critical nature of WBANs, where both data and power must be managed intelligently. For wireless power transfer, various driver circuit classes exist, from A to E. Our research focuses on the saturating Class C driver. Based on our previous work, we found it to be more efficient than others like Class A or B. It offers a good balance of performance and stability for our application, though we will later propose an improvement to its common design. Therefore, the objectives of this work are clear. First, to model a WBAN system specifically for an inductive power transfer circuit using a saturating Class C driver. Second, to develop a novel scheduling scheme for efficiently charging the wireless sensor nodes within this WBAN. The fundamental principle we use is inductive power transfer via electromagnetic induction, similar to a transformer. This allows power to be transferred without any physical connections between the source and the load, which is ideal for implanted or wearable sensors. We chose inductive powering for wireless energy harvesting because it is reliable, not dependent on specific environmental conditions like sunlight, uninterrupted by objects in the near field, and its power flow is easily manageable through electronic control, a crucial feature for implementing our scheduling algorithm. This is the circuit topology of the saturating Class C driver we employ. It's a current-fed topology preferred for stable magnetic flux distribution. The block diagram traces the path, from a DC source, through the driver and primary inductor, across the wireless link to the secondary inductor, through a rectifier, and finally to the sensor node load. Designing the system requires careful, iterative parameter selection. For the secondary circuit, we start with the load requirement and iteratively select components like the coil and capacitor to maximize the quality factor. The primary circuit design is then optimized based on the finalized secondary components, with the goal of maximizing driver efficiency. This ensures the overall link is optimized for power transfer. Here is our key hardware contribution. In the existing design, two MOSFETs are used in parallel in the driver to handle current, but this increases switching losses. Our proposed model uses a single MOSFET. We select a MOSFET with a drain source voltage rating at least 10 times the source voltage. This increases current handling capacity, improves performance during startup in rush current, and, as we will see, reduces overall losses. For our simulation and design, we made specific, practical assumptions: a telemetry unit with a 6 mm solenoid, consuming 4 mA from a 4V supply, with a maximum wireless power transfer distance of 70 mm. This defines our test case scenario. This is the actual circuit we built in the SPICE simulator using our proposed single MOSFET model. The key parameters are a 1 MHz operating frequency, a 0.71 coupling coefficient, and a 10% duty cycle for the pulse driving the MOSFET. Now, moving to the software intelligence, our scheduling algorithm. It is demand-based, triggered by the controller. Its purpose is loss mitigation. The condition to start charging is when a sensor node's voltage falls below a threshold, which we set at less than 10% of its nominal voltage, following IEC standards for critical systems. This slide integrates the hardware and software. The controller runs our proposed algorithm. It monitors the secondary side sensor nodes. When the algorithm dictates, it sends a signal to switch on the wireless power source from the primary side, initiating a charging cycle in a coordinated manner. This is the core of our scheduling logic. Let me walk through it. The controller continuously monitors node voltages. If a node is predicted to drop below the threshold within 6 cycles, it's flagged. If it can't support the next 3 cycles, it gets priority charging. Otherwise, the algorithm intelligently schedules charging during the node's idle data transmission periods to avoid interference. If data arrives suddenly during charging, it pauses and resumes. This ensures data integrity is never compromised for power transfer. Now, let's examine the simulation results, beginning with the impact of our scheduling algorithm on the existing double MOSFET driver circuit. The top graph shows the continuous power consumption of the traditional, non-scheduled approach. You can see it constantly draws a high level of power, around 60 to 80 milliwatts, to maintain the sensor node's voltage at the nominal 4V. The bottom graph demonstrates the effect of applying our proposed scheduling algorithm. Instead of continuous power transfer, it activates charging only when needed, resulting in short, periodic power pulses. This drastically reduces the average power drawn from the source, directly extending the primary battery life. Moving to our improved hardware design, this slide shows results for our proposed single MOSFET driver circuit. The top graph again shows the non-scheduled, continuous power consumption, which is already lower than the double MOSFET version. The bottom graph showcases the powerful combination of our new driver circuit and the scheduling algorithm. You can observe a further significant reduction in the amplitude and duration of the power consumption spikes, maintaining the node voltage at or below the nominal level very efficiently. This visually confirms that our single MOSFET design is inherently more loss efficient. This final results slide provides the conclusive, quantitative comparison. The bar chart aggregates the total power consumption for our key scenarios. The left set compares the double MOSFET driver with and without our scheduling. The right set does the same for our proposed single MOSFET driver. The reduction is dramatic in both cases. The table provides the exact numbers. For the single MOSFET circuit, the unscheduled consumption is 0.116 megawatts. Our scheduling algorithm cuts this down to 0.049 megawatts, a reduction of over 57%. Most importantly, compare the final columns. Our complete proposed system consumes less than 1/8 of the power of the old, unscheduled system. This proves the synergistic efficiency gains from both our hardware innovation and intelligent scheduling software. In conclusion, this research contributes a system model for WBAN using an improved saturating Class C driver, a novel scheduling technique for charging, and a comparative analysis showing our combined approach is far more efficient. The main prospect for future work is the hardware implementation of this developed technology to validate our simulation results in a physical prototype. The development of the scheduling scheme for efficient wireless charging of sensor nodes in WBAN is an ongoing process, and we welcome any suggestions or insights. If you have any questions regarding this work or are interested in collaborating on future research in this area, please feel free to contact the authors via the provided email addresses. Thank you for your attention and interest.